Well, thanks everybody for showing up this evening, afternoon, morning, whatever it is, where you're at in the world. Um, so this is the annual Juneau Icefield Research Program student presentation hosted via the IGS webinar platform. So my name is Chris McNeil. I'll be the EMC master clicker of slides tonight. And we'll just be cycling through. First, Seth will be giving a quick intro to the program, and then we'll be going through the various student projects, followed by a Q&A session at the end. So if you want to just hold off your questions till the very end, that would be great. For those of you presenting, if you could just say next slide whenever you're ready for the transition, that would help me move things along. So I guess with that being said, it's on to Seth Campbell.
All right, thanks, Chris. So thanks everyone for attending today. My name is Seth Campbell. I'm the Director of Research and Academics at the Juneau Icefield Research Program, and my colleague Annie Boucher is a Director for Operations. So we kind of lead the team from all the happenings that we have on a yearly basis. I'm just going to give a little background about the Juneau Icefield. Before I do that, I do want to acknowledge that that JIRP operates on the unceded territories of the Aquan on Tlingit Ani, which we also know as Juneau, Alaska. And we acknowledge that the Tlingit peoples have been stewards of the land that we work on since time immemorial, and we're very grateful for their stewardship and incredible care of the land. Ganesh Shish. JERP's been operating on the Tlingit lands for about 75 years. This is our 76th year that we've operated. And the primary program operates in June through August as a summer program. It originated in 1946. And over the past 7 decades, we've had roughly 2,000 people on the ice field for various reasons as students, educators, research scientists working together collaboratively. So the students you're going to hear from today are the primary JERP students that were on the ice field for this summer, an incredible group. I feel very honored to work with this group. It's truly the honor of my life to work with this program. The quality of people that we have working with us and the camaraderie that's built on this program is pretty phenomenal. On top of the primary program, I did want to mention a few things. We're growing a bit. We've started a new program supporting high school students, working with the U.S. funded Department of Education funded Upward Bound program. Upward Bound supports roughly 70 to 80,000 low income and what will be first generation high school students across the United States. So we had our first couple programs this summer, and we're planning on, so far we have 5 programs lined up for next summer on top of the regular JERP program. So keep an eye out for that. Next slide, Chris. So the ice field itself is roughly 4,000 square kilometers in area. You're going to learn a little bit about that today, but I figured I'd show a couple camps. The picture on the upper right-hand side is Camp 10, and it has about a capacity of about 70 people. And the picture in the bottom right is Camp 18. It has capacity of about 50 people. And the only other thing I wanted to mention today is that we're pushing towards turning the ice field into a quote-unquote new polar earth and planetary sciences proving ground and training program. The idea being that we want it to be kind of a melting pot and a meeting location for scientists, educators, and students to meet together, work together, pool resources together, and collaborate on polar science ideas. Currently, we have funding from NSF, NASA, and the Department of Defense through the United States, but we certainly welcome international colleagues as well. So the picture on the left-hand side, you can see those dots represent field stations that we have. The yellow dots with X's are the Camp 10 and Camp 18 locations. Next slide, Chris. So with that, I encourage you to reach out to me if you have any questions about this, the ice field as a community resource. Always happy to brainstorm ideas of how we can build collaborations, build more opportunities for students. That's what we're all about, is trying to build opportunities for students. So with that, I think I'm going to pass it over to students and look forward to hearing what they have to say about their research this summer.
Thank you, Seth. So what I will present to you is about first
why do we study the Juneau Icefield, and especially what this means for like the vulnerability to climate change. I'm Andreas Hens. I'm a master's student at the Department of Earth Sciences and doing mostly glaciology and paleoclimatology at ETH Zurich in Switzerland. So how would like to show you what the vulnerability of the Juneau Icefield is and how special it is in terms to climate change. Is with a very simple model. The model I used already at some courses at the University of Zurich. So what you see in the middle is like a very schematic and idealized profile. I will go through that and show you the different stages where we are in the ice field, etc. On the very right is a picture how, yeah, it's from Seth, stolen from Seth, thank you. How the depth of the Taku Glacier, showing that like most part of the ice field glaciers are quite thick in the middle. And yeah, the lower right picture is just that for this model, we only use a shallow ice approximation, which means that we neglect all longitudinal and transversal stresses, just like the verticals. So on the next slide, you see this very schematic, idealized Juneau Icefield again. We start at the top, and the top we have like this, yeah, some mountains that are 15 meters above sea level, or sometimes 2,000 meters above sea level, where the glacier starts. Then on the next slide, you see the very flat part of the Juneau Icefield, which is really, really flat, even flatter than on this scale here, because the y-axis is over-exaggerated according to the x-axis. And after the very flat part, which is about 10 to 20 kilometers long, here a picture of Taku Glacier, where we have been, comes the steeper part. This is in the next slide, a picture of like how a steeper part looks like. It can also be less steep, possibly. And at the very end, at the tongue, you see also a picture of that is like the, for example, Mendenhall Glacier. So what you see as a bedrock feature here in the middle, this little bump at about 1,200 meters is like not really a dam, which would dam water like building a lake. It's more like a gorge-like feature where the bedrock is, the valley is narrow and kind of dams the ice behind that. What you see now in this two red lines are two equilibrium line altitudes, the ELA. The lower line is the ELA at pre-industrial level, which means like before we had like, yeah, climate change and before there were so many humans on the world. And the second line, the solid line, is a second ELA, which I give into the model as like a forcing of about 0.6 to 1 degree Celsius, which is equivalent to about 100 meters change in ELA. So the ELA, in general, just a quick reminder, is that above this ELA we have accumulation, so the glacier gains mass, we have more snowfall than melt, and below the ELA we have the ablation area, so the glacier loses mass and yeah, melts there more than it snows. So let's see what the model gives us if we shift the ELA from the lower part. This is now the picture what you see in the glacier form. You see it was done with the lower part with the dashed line, and then we shift instantly to the solid line and look what the glacier does or what the ice field does in this model. On the next slide you see a quick, oh maybe go next, yeah, this one, thank you. So what you see here, like ELA is coming right on top of the part where the ice bed, the ice field begins to be very, very flat. And as soon as the ELA is in this very flat part, there is of course a lot more area that comes into the ablation area. And with this, also the whole level of the ice field goes a bit down. And this means that even a bigger part of the ice field itself comes into the, below the ELA, which means we have some kind of a positive feedback loop. As soon as we are below the ELA, we have a lot of melting. This means about 90% of the glacier can melt back if we only go like 100 meters higher with the ELA, according to this model. yeah, this is in general the question why it's so interesting to study the Juneau Icefield, because we have this high vulnerability to climate change. And there's a second thing. If we have if in the model we go back to the old ELA with the last glacier we have in this video. If you go back to the old ELA, the dashed line, what will happen then, and will the glacier grow back as far as it was before? You see this on the next slide. So now we're growing back from the solid line, from the dashed line to this back to the solid line. And what happens that we only have like the glacier doubles a bit in length. To go back to the glacier we have now at the moment with the whole valley filled with ice, we need to go even 150 meters lower than it was pre-industrial just to build up the ice field again, which means like this is kind of this hysteresis problem we have in also, of course, in other places in the world with ice sheets, etc. And also the Juneau Icefield has this apparently. Okay, thank you very much for listening.
Right. So up next we have Anna.
Okay, great. Thank you, Andy, for that presentation. So hi, everyone. My name is Caroline Wexler. I was a student at JIRP this year. We're all really excited to be here, and we just wanted to thank IGS again for letting us present our work to you all today. So my group studied the water isotopes from past snow and fern cores on the Juneau Icefield to look at the interannual variability. Next slide. So why do we want to study water isotopes on the Juneau Icefield in the first place? Well, first off, Alaskan glaciers are one of the biggest contributors to global sea level rise. In addition to that, we can constrain local climate variability to analyze atmospheric temperature and circulation trends on a local level. And lastly, we can also understand the dynamics of glaciers transitioning from a cold and stable state to more temperate and sensitive. And this is really important because temperate glaciers are right around the melting point of water. So any slight increase in temperature is going to drastically affect the way that they respond. Next slide. So this is just a figure showing visually how the mass budget loss of all the glaciers in the world are responding right now. So we can see by the size of the red circle how much of that is actually being lost. And we can see in Alaska, the circle is pretty big. So Alaska is losing, again, a lot of their ice compared to the rest of the glaciers in the world. And next slide. And this one is, again, showing a similar result, but it's a bit of a newer figure. And so we're also getting some specific numbers here. And we can see that Alaska is losing about 66.7 gigatons of their mass balance per year. And compared to like the global amount, this is about 1/4 of all the glaciers in the world. So it's a pretty significant number. Next slide.
Okay, hi everyone. My name is Jason. I'm a laboratory technician at the University of Vermont, and I was also working on the isotope project this summer. I'm going to talk a little bit about the background of isotopes and how to apply them. And so this is going to be a little bit of a deeper dive, and we're going to do a tiny bit of math here. So just bear with me, and hopefully this will make sense in a few minutes. So stable water isotopes have been a central tool utilized by polar scientists in paleoclimate studies for decades. The method is dependent on an empiric correlation between water isotope ratios and precipitation and surface temperatures. Transport of moisture by the climate system, removal of water by precipitation, and isotopic fractionation during phase changes all alter the ratio of oxygen and hydrogen isotopes in water. Utilizing the measured ratios, it's possible to reconstruct condensation and initial moisture conditions if the relevant scaling relationships are accurately constrained from theory, models, and natural observations. Initial work on this topic was pioneered in 1964 and has been progressively improved since then. Compilation of all of the delta deuterium, which is hydrogen isotopes, and delta O18 oxygen isotopes values measured at ice cores in Antarctica, as well as data from the global network of isotopes and precipitation is the figure on the right here. This suggests an almost linear relationship between the two isotopes. However, fitting a best fit line to the data indicates that although for very basic approximations, a linear relationship may be sufficient, it is truly more complex than this in nature. Interestingly enough, also when you color the data based on where it originates from, the JERP isotope data fits a gap in between the GNIP and the Antarctica data. So I think that's kind of interesting. Okay, so how do we go from isotope ratios to temperature reconstructions? If you want to go to the next slide, Chris. So to reconstruct condensation site temperature and evaporation site temperature, multiple constraints are needed. These are provided by oxygen and hydrogen isotope ratios, as well as the ratio between the two measured ratios. Deuterium excess is the linear weighted difference between the two isotopes. This is problematic because, as we saw before, that relationship is not perfectly linear. So better methods utilize a nonlinear approximation between the two isotopes. But further, this method utilizes a pair of equations which solve for the condensation site temperature and evaporation source temperature. Those equations are on the left there, where beta and gamma are the values that you need to solve for. The problem with this is that those values are also dependent on the site temperature and source temperature. So you get sort of a circularity problem where you can't actually solve those equations without knowing what the reconstructed value is that you're trying to solve for. So our advisor, Brad Markle, created a simple water isotope model which applies simple physical principles to model the isotopic fractionation of water down temperature and pressure gradients as it's transported by Earth's climate systems. And that's what these state space plots are on the right. And so one axis is the condensation site temperature and the other axis is the evaporation temperature. But again, what you can see is that there's not a simple relationship between them. So around -30 degrees for condensation, for example, there is either a saddle or a change in slope for most of them. And so even using the nonlinear relationship, which is the bottom right one, we're still not able to accurately reconstruct the temperatures without some issues. So how do we solve this? If you want to go to the next slide. The last complicated figure here. So what our advisor Brad did is he inverted the state space plots with respect to the input parameters, which results in a map of the condensation site temperature and the evaporation source temperature based on the isotopes themselves instead of the other way around. And so, for example, if you have a sample that has a nonlinear deuterium excess value of 12, which is the y-axis, and a delta O18 value of -26, which is the x-axis, then you can reconstruct the condensation site and evaporation source temperature. And so next, Anna is going to talk about some of the methods that we use to apply this model to this summer.
Hi everyone, I'm Anna, and I'd love to talk about our methodology for just a few minutes and what we use to answer some of our big questions. So our methodology for this project really focused on acquiring both spatially and temporally resolved water samples for isotope data. So there's been series of shallow firn cores for this purpose taken from the Juneau Icefield in multiple locations since 2012. And we wanted to continue that record using those geographic locations. We manually drilled up to 10 meters, sampling 10 centimeters of every 40. You guys can see that process in some of these pictures on the slides. And we were able to sample the same way in some of the JERP mass balance pits, which were already dug. This was a pretty excellent additional use for another long-standing independent project that JERP does, which was kind of cool. So once all of our samples melted, we took aliquots of each well-mixed core sample for laboratory isotope analysis for those deuterium excess and delta O18 values. We used them in conjunction with each other, as Jason was mentioning, with the SWIM model to analyze both the condensation site and evaporation source temperatures. And generally, as we saw in that linear plot, as both delta O18 and deuterium excess values become more positive, both evaporation source and condensation site temperatures increase. So this is kind of a way that we can easily check ourselves as we go along, even if we don't know the exact values yet. The Earth's latitudinal temperature gradient and ocean atmospheric circulation patterns also impact evaporation source temperatures. And this allowed us to tie weather models to our isotopic sea surface temperatures that we got from the ice field firn cores. So we used independent meteorological data in the high split model, which allowed us to reconstruct storm circulation patterns and identify the geographic location of moisture sources. So this methodology allowed us to compare trends in storm tracks and sources of Juneau Icefield precipitation over the last decade, which helps us understand how Earth's climate system is changing in real time. And that's a perspective we really want to continue using as our data set continues to expand in the coming years as JIRP continues to run through the summers. Next slide.
Hi everyone, I'm Fabi. Same as Andy, I'm from Switzerland and studying at ETH. I'm doing my master's in environmental science. Now I'm going to continue with the results. So the first figure here shows the range of the reconstructed temperatures of the year 2017 in purple versus the measured temperatures at Camp 18 in blue. The black line is the reconstructed mean condensation temperature. So the figure shows that in winter, the reconstructed temperatures are within the same range as the measured temperatures and therefore validates our results. Next slide, please. Okay, on this figure, it shows the depth in centimeters on the y-axis versus the mean annual condensation temperature on the Juneau Icefield on the x-axis. The orange line shows the temperature values for the year 2017, and the blue line the values for the year 2021. And the green line shows the mean condensation temperature for the year 2016. For the comparison of the different years, we only included the top 300 centimeters, as you can see in the figure, because we have less data points deeper down in 2016 and 17. Also, the figure here generally shows the early winter, but there is some uncertainty with it as we have the snow starting to fall in October until April and May. But then we also have the melting. Okay, so now let's have a closer look at the figure, as there is quite a lot of things happening here. So first of all, the trend in temperature versus depth is really cool to see here. So near the lower depth, closer to the firn ice interface, the temperatures are higher than above, which might reflect early season precipitation during the late fall or early winter, before the temperatures have fallen to their lowest during the middle of winter. And then if we go a bit further up, at around 100 centimeters, the reconstructed condensation temperatures reach their lowest point, and then they seem to begin rising slightly. But that might also just be variability in the data. We think that the reasons we do not have data for late winter and spring accumulation is because it melts before we are able to collect it. We observed this year that the melt is really high on the Juneau Icefield, so most of the late season snow is not able to be measured because it's gone before we get out there and collect it. Then if we look at the annual variability, the comparison of the mean temperatures of 2017 and 2021 shows that there is a warming trend of 0.58 degrees. We compared this, calculate the change to reanalysis data for the same years. And obviously the reanalysis data has a way bigger grid, but still it shows us that the change is in the same order of magnitude. So this is pretty cool to see how the ice field is accurately recording the variability. And then also, if we compare these years to the year 2016, we can see that it has the highest condensation temperature from all the 3 years. And this correlates with measured weather data, which shows that 2016 was just a very extremely warm year. And the year 2017 was really cold. So it seems like we have a really good record for the annual variability here. To sum up, I think it's important to notice that we have a very small data set here in a regional climate. So with our data, we cannot say anything about general warming trends, but we can clearly see that the ice field is a pretty good record for annual variability. Next slide, please.
Okay, so continuing on with the results, like Anna had mentioned, another way that we also wanted to contextualize this data was to use the weather model called high split. And this was to find where the winter storms and the moisture originated from before it precipitated onto the Juneau Icefield. And this allowed us to see how those moisture sources were varying temporally and spatially. So we ran back trajectories every day of 2017 and 2021, and we got a ton of back trajectories back, and decided to cluster the 7 most frequented pathways that air parcels would take. And so in 2017, if we're just looking at the winter months here, so on month 12, 1, 2, and 3, we can see that the highest frequency pathways were pathways 6 and 3 in the dark blue and the light blue lines on the left. And then if we're looking at the right with the map, we can see that these pathways 6 and 3 originated in Siberia, Russia, and in the Arctic Circle. So it's really interesting to note that both of these pathways originated in higher latitudes. Next slide, please. So again, we did the same thing for the year 2021. And what's really interesting here is to see that almost 45% of all of the winter storms originated with just pathway 7. And we can see that pathway 7 originated in Arctic Canada. So while in both years, both 2017 and 2021, these winter storms originated in high latitudes, it's interesting to see the difference longitudinally in the Arctic Canada versus Russia. Next slide.
All right, so we'll just run through a couple of our main conclusions one more time. So the Juneau Icefield is important for isotope studies due to its unique glaciological setting. It's temperate, it receives high precipitation, but also has relatively high temperatures. So it's melting quite a bit, and it has a high amount of water that it's providing to sea level rise. And then our reconstructed temperatures from past years appear to accurately reflect recorded meteorological data and reanalysis data. And they're also reflecting annual variability in the climate record pretty accurately for the local Juneau Icefield climate. And we also did some storm source tracking, which was modeled to compare to evaporation source temperatures. If you want to hear more about this, come check us out at AGU. We're going to have a poster there, and we'd love to be able to talk to you more about it. That's it. Thank you all.
Alrighty, thanks a lot for that. Up next, we have Kitzel. They will be discussing ground penetrating radar work on the Juneau Icefield this summer.
Yeah, hi. So my name is Kitzel Lusted, and I'm just finishing up my undergraduate degree at the University of Utah, where I'm studying material science engineering. And I'm going to talk about JIRP's use of GPR to study fern aquifers in the past and how we used it in the 2022 season. So next slide, please. Right. So as the Ice Core group highlighted, studying the way water moves on the Juneau Icefield is important because of its contributions to sea level and the downstream effects that can have. To that end, JIRP has used GPR quite a bit to study the Juneau Icefield, and the most recent repeat study of the Juneau Icefield has been on the Llewellyn Ice Divide, where in 2018 they discovered a fern aquifer. On the slides, we see the 2019 results of that same aquifer. The scan was able to identify several ice lenses near the surface and the aquifer, which started about 3 meters below the surface. The ice core group corroborated the GPR results by drilling a shallow core at the ice divide. From this core, they were able to identify several of the ice lenses and the aquifer itself because the core came back absolutely dripping with water. When they did this in 2019, the GPR group noticed that the Fern aquifer was smaller than it had been in 2018. And in this past season, in 2022, we supported this claim when we came back and we couldn't find the aquifer using GPR. So considering the change between 2018 and this past year, the aquifer at the ice divide may have drained or refrozen in the time between scans. So next slide. So what we did do this past season was take a GPR scan of a really interesting hydrologic feature near Camp 10, which is on the Taku Glacier. After an extended period of really high temperatures for the ice field, which were around 26 C for several days, we noticed several of these superglacial hydrology features forming on the glacier. As seen in the far left picture, they formed like rivers and kind of pooled in depressions as lakes. To better understand what was happening with these features, we did a series of GPR scans. So we started at one of the mass balance pits and we did a GPR scan from the pit to the edge of the lake, and then one around the perimeter of the lake. And then starting on the far side, we returned back to camp. So next slide. So the results of the first 2 GPR scans, so the one going from the pit to the edge of the lake and then around the perimeter of the lake, are seen on the left and right respectively. The measurements we took for this scan were backed up by visual images of the feature, so we were able to ski right up to the edge of the lake, and then at the point where we skied up to, we could see that it dove beneath the surface. And this corresponds to the results that we got, where the water table starts really low as we were at the mass balance pit, of which we did not hit water at this mass balance pit. And then as we skied closer to the lake, the water table jumps right up to the surface. So although we didn't get to image the Fern aquifer that had been seen in 2018 and 2019 at the Llewellyn Ice Divide, we did get to look at a really interesting feature that no one had seen before on the ice field in this area. And I think it's going to be really interesting to see if this reappears in the future or if this was a one-time sort of deal caused by really high temperatures this year. From this season, we learned that the Juneau Icefield has highly spatially and temporally variable hydrology, with the old aquifer at the ice divide being gone and a new aquifer appearing or being discovered near Camp 10. I'm excited to see what other hydrological features the Juneau Icefield has in store for future JERPers. Thank you.
Excellent. And up next we have, let's see, Indigo. And they will be discussing the art and science of Juneau Icefield this summer.
Hi, I'm Indigo. I'm a student at Monash University in Australia, and along with Megan, we're going to talk a bit about science communication and community engagement within JERP through the lens of science and art collaboration. Can I have the next slide, please? So we want to share a learning experience we had on the ice field this summer that utilized cyanotype to investigate and highlight the physical properties of a fern core that we collected. So we've got 4 main sections in our presentation today. I'll give a bit of background about fern cores and cyanotypes. I'll talk you through some of our processes, and then I'll hand over to Megan, who'll discuss co-production and the opportunities it might present to you as science educators and communicators. We'll then have some time for any questions you might have. Can I have the next slide, please? So the key to our presentation today is the cyanotype tapestry you should be able to see now. So cyanotype is a photosensitive chemical regarded as one of the earliest forms of photography. And we were introduced to the cyanotype process by Hannah Mode, one of our teaching faculty this summer. Hannah's also a wonderful artist and educator, and you should check out her website that we've included at the end of our presentation. So cyanotype is water fixed, meaning that the dye is set when rinsed with water. And when you bring ice, fern, or snow into this process, you get some really interesting and beautiful patterns that begin to emerge on your materials. Can I have the next slide, please? Yeah, so our tapestry was created using leftover pieces of a fern core that we collected for isotope sampling. And this initially sort of began as a fun activity reflecting on our day of drilling, but it's become a really useful science communication piece. So we used our tapestry in public presentations in Atlin and Juneau, and it became a really useful conversation starter for engaging non-glaciologists, sort of like a visual hook for people that didn't have any context to what we'd been doing over the summer. But beyond being visually interesting, the process of creating our tapestry also allowed us to think more deeply about the ice field and its structure. Can I have the next slide, please? So the fern core segments we used were collected using a hand drill from the bottom of a mass balance pit that we dug on the Taku Glacier. The core was collected in 20 centimeter segments that were then weighed for density and cut in half for isotopic analysis. So we took the leftover pieces of fern core back to camp, and after they were admired by everyone, we had the idea to utilize them to create a piece of art. So the pieces of fabric in our tapestry were laid out on a slope, and we arranged the fern core pieces in order of depth before leaving them to melt and interact with the cyanotype dye. After the core had melted, we rinsed out the fabric and stitched the pieces together to create our tapestry. So I'm going to hand over to Megan now, who'll talk a little bit more about the details in our tapestry before discussing the co-production process.
Hi everyone, my name is Megan, and as Indigo was mentioning, we created this tapestry from part of a fern core, and we were able to see some visual things in our tapestry that were kind of interesting. We were able to see the rectangle where the core had initially been placed on the fabric. We were also able to see, some fuzziness around it where the melt had started happening and the water was being absorbed into the tapestry. As well as we had a channel that had been packed with snow that showed sort of water or melting over time. So although we saw representations of elements that create a fern core, we saw some other uses in this exercise as well. One of the main ones that Indigo touched on was that it can spark discourse. So both amongst ourselves after a day of field work, but also as an entryway to discuss fern and ice cores with those outside of this experience or those outside of our field. We also saw this as a way to aesthetically represent our experience. So you can't take a fern or ice core home with you, but you can take a print of it. And so this became a really useful tool for us to continue discussion of our learning off of the ice field. It was a piece of our experience we could take with us. And Chris, the next slide would be great. So co-production is a term that I've been thinking a lot about since coming off of the ice field as I reflected on this exercise. And it's a term that I've been seeing more and more in the literature and in earth science. There's a few different definitions, but one that I've really liked is that co-production utilizes two or more disciplines or lenses to understand and investigate a topic, and the equality of these disciplines in the creation of co-produced knowledge is an important element here. So in our experience with this tapestry, we were able to use both art and science to explore our understanding of these cores. So like one of the previous groups was explaining, we were able to use science to look at the isotopic signatures of the core. And as this project shows, we were also able to use art to understand some other elements of this core, including sort of an emotional connection to time and place. And we were able to use both art and science to understand how these cores form and as data points to communicate this understanding to those outside of our experience. So in the literature, co-production has been shown to broaden the audience that science can reach. It allows different entry points into scientific research. It also allows us to access more subjective lenses like these emotional responses to phenomena, which feels really important to me in the realm of climate science. And it can increase engagement and people's personal connection to topics as it allows for cultural and contextual backgrounds to inform our understanding of our scientific research. So I've talked a little bit about how co-production can be used as a tool for education and engagement, but it can also be a great tool for scientists themselves to understand their own research on a deeper level. An example of this that I found in the literature was a study done by Tosca et al. In 2021, which will be cited at the end of our presentation, where scientists from a jet propulsion lab were paired with designers. And these designers and artists created a visual interface for the data the scientists were collecting. And this was shown to increase the number of unique insights that scientists were able to identify because they had this tool that was really easy to use and visualize their data in a novel way. So overall, co-production is a great way to increase engagement with our work, to educate others both inside and outside of our field. And it's also a tool for us to understand our own work on a deeper level. I've talked a lot about art and science as a pairing for co-production, but of course, co-production is a lot broader than that. It's this transdisciplinary approach that pushes for a more holistic understanding of a phenomena. And that can take a lot of different forms. Another example I've been seeing a lot of in the literature is the inclusion of Indigenous knowledge systems in scientific research. So it doesn't just have to be art, but it's just a way to explore all these different avenues into our understanding of what we're researching. Yeah, and like Indigo mentioned, this project was really inspired by Hannah Perrin-Mode, who is a great example of the ways JIRP is pushing to include professionals from a diverse set of skills and to really give students a more holistic understanding of the ice field by providing avenues for us to explore our understanding through things like art. And on a personal note, I'm a student with a background in environmental science. I've always sort of studied science from a very physical, traditional lens. And so having this opportunity to try out a more creative way of improving my understanding was really, really fun. Yeah, next slide, Chris. So we've just got a couple of photos from the day we were putting this all together. And next one, I think, is just a little thank you. So thanks for listening. I both have our emails up here if anyone wants to reach out with any questions. And then the last slide is just some further reading if anyone's interested in what we've been thinking and talking about beyond this presentation. Thank you.
Excellent. Well, thank you all. Up next, we'll have Annie. We'll be talking about how to apply for JIRP, either as a student, staff, or faculty.
Perfect. We go to the next slide, Chris. How to join JIRP. JIRP thrives on participation from the earth science community, the polar science community, and people like all of you. We want more people to get involved. All of the information about JIRP you can find at juneicefield.org. Chris, will you turn the slide? Specifically, we divide participants into a couple different categories. Our student applications are open now. These are open to undergraduate students primarily, but also graduate students who are interested in getting some hands-on experience in the field. Our students get 6 credits through UMaine, this should say, or through the University of Alaska Southeast. They spend 8 weeks in the field, which is an extraordinary experience for a lot of students during their undergraduate career. They get a wide range of faculty contacts. They often meet up to 30 to 40 faculty over the course of the summer. And that network has shown to be critical for a lot of students in our field. We teach at about a 200 to 300 level academic curriculum, and we give full instruction in backcountry skills required to traverse the ice field. We accept students who have never seen snow. We accept students who have never slept outside. We accept students who cannot ski yet. And we bring them all across the ice field in a very fun fashion. Chris, will you flip the slide, please? Our applications are also open for teaching faculty right now. So these are PhD students, professors, researchers, professionals in their fields, they volunteer to come to JIRP primarily to teach our curriculum, which includes both lectures that we ask people to give beforehand and lectures in each person's area of expertise. Lectures, workshops, field trips, really the sky is the limit. We are open to creative pedagogy. It's a 2 to 3 week time commitment, including 2 weeks in the field. And we provide room and board, safety training, and mentorship, especially to early career faculty who we love to have at JERP. Next slide, please, Chris. The final category for which we are soliciting applications at the moment is for research faculty. We provide logistic support for funded fieldwork. We provide safety staff, we provide field equipment, we provide logistic planning. We have a wide range of people who have been working on the ice field for over a decade, and they have a robust understanding of different areas of interest for different science questions. And we have a deep pool of potential field assistants who would love nothing more than to see some real research happening in real time. We are excited about cost sharing options, sharing helicopters, sharing tents, et cetera, et cetera. JIRP is a collaborative atmosphere. We hope that everyone comes up, is excited to cooperate with everybody else who's up there. And again, we try to provide as much mentorship as we can for early career scientists. I think doing research, testing tools and methods, training people for work in the field are all a lot easier at JIRP than they are in other polar regions. It's domestic. We're 2 hours away from Seattle. You don't need a passport. It's a great place to come do some low stakes field work. So if you have any questions about students or teaching faculty or research faculty positions, those are all open now. The information is on the website, and Seth and I are always available to answer any questions. Seth, do you have anything you want to add to that?
I think you nailed it, Annie. Thanks.
Thank you. Seth and I will also both be at AGU. So if anyone cares to accost us in person, that's going to be the next live appearance. That's all I've got, Chris. I think we are open for questions now. Oh, sorry. Next week, IGS seminar. Dr. Nandan from the University of Manitoba is giving a talk on snow, a villain that impacts sea ice, geophysical retrievals from radar remote sensing, and Dr. Hobbs from the University of Tasmania is giving a talk on something that's cut off, reasons for increased Antarctic sea ice variability. I hope you all tune in. Those are sure to be exciting. And I think that is all I have. Next slide, Chris, just to make sure.
I think that's it.
Thank you, Tavi. We appreciate your audience. We appreciate everyone coming today. A big shout out to all the hard work the students put. And Hannah Verbancourt is on here. She had a huge hand in organizing all of this today, and she is our unsung hero of the week. So thank you, Hannah.
Excellent. So before we open things up for questions, I would like to just promote the first of all, thank you all, the students of the program, for collecting the mass balance data from the Juneau Icefield this summer. It's amazing. We rely on folks like yourselves to continue this legacy data set. Unfortunately, due to US Geological Survey policies, I'm unable to say anything about the results from those data just yet, but in about 2 to 3 weeks, we keep an eye out on the Glaciers webpage of the USGS. You will be able to download that data. Our data release containing the 2022 data will be coming out, so keep an eye out for that. So with that, I'd like to open it up for Q&A.
I definitely have a question. Oh, Sam, go for it.
Hi, Kitzel, I just have a question for you about the signatures that you were observing in the fern aquifer. I'm curious if you guys saw any sort of impermeable layer under the feature that had a similar slope, or if there wasn't any, there was just a transition back to fern below the aquifer you guys were observing.
All right, thanks, Sam. So the type of radar that we were using didn't have a long enough wavelength to get really below the fern aquifer. Because there was so much water in that area, we were getting way too much reflectance and scattering back off of the fern aquifer that we were seeing. But that would be interesting to go back there and with a longer wavelength and see if we could get down deeper.
And just sort of a similar question, do you know if there were any cores that were drilled along that transect this year?
On the transect from Camp 10 area?
Yeah, from 10 out towards the superglacial lakes.
There, we didn't drill any cores out there. I know they did a couple cores, which might be a better question for the ice drilling group, near the ice divide. They did some more cores near there, but we didn't do any at the Camp 10 aquifer. We did dig a mass balance pit there, and we did some like the normal density measurements that we had.
Thanks, awesome stuff.
Indigo said a fern core was taken near the mass balance pit near Camp 10. Indigo, do you know if I seem to remember, there's not a lot of fern left by Camp 10. It's fairly thin at that area.
Yeah, from memory, we got maybe 2.5 meters of fern before we got stuck in ice.
That was the ice stuck location.
Yes, that was that day. So yeah, that data is definitely somewhere. If people were interested in that, I would have to go digging for it there.
It's I have a question for Andy. Andy, can you kind of illuminate what impacts to your model you might think the additional tidewater component of Taku Glacier might be?
Okay, yeah, that's something I completely did not tell because just going too far into rabbit hole then. I mean, as soon as we have like a glacier calving into seawater or a lake, it's even retreating even faster, I'd say. So as we saw, like most part of the Taku main branch, the bed is lowering below sea level. So we expect there to have really a lake or even a seawater. So I would say like the retreat is even faster than my model gives as an answer.
Do you think potential stabilization and then re-advance giving a lowering of the ELA would be kind of comparable, or
would be
a little bit different?
What is the question? If it's now or like afterwards it melted?
Like one of your final scenarios showed if we lower the ELA down to pre-industrial levels, I think was the term you used. Given the tidewater nature of that glacier, do you think your model would do the same thing or potentially something different?
I would suggest, like, I mean, you can never reach to the state that was before, or that, well, how it is now, the Taku Glacier, for example. So I'm not really sure what happens if like you have an advancing glacier going into tidewater and maybe also like putting a lot of sediment in, maybe filling it up again, possibly. I'm not really sure what happens there. And I mean, the model is way too less sophisticated to show such things. I'm sorry that I don't really know what what you're expecting.
No. That's awesome. Thank you so much.
You're welcome.
Actually, just bouncing off that really quick for a second, did you run any simulations to show what ELA would be necessary for re-advance to the current state after a retreat?
Yes, actually for like building up the glacier, the model always starts with just bedrock. So building up the glacier, I needed to go to like 150 50 meters even lower. So I have it on 950, so I needed to go down to 800 meters to build up the glacier like that. And then I can go up to 950 meters above sea level, and then the ice field stays like that. And as soon as I go 100 meters higher, then it melts back all the way.
So I guess I have a question for Caroline, Jason, Fabi, or Anna. What next with the isotope project based on these results that you have? Have you discussed next steps?
I guess I can jump in here. So I think our next step is that or Brad is gonna process all the samples we collected from this summer. So they had some lab equipment malfunctions that have prevented them from getting any of the data from any of the stuff we did this summer yet. But once we get that, I think we're going to start looking at what that's telling us and try to compare to a few years, because we have snow, fern, and ice samples from every year back to 2012, except 2020. There's only like 4 samples or something like that. And then there's also the deep ice core from 2019. And we want to look at that because it does this interesting thing right at the where the fern aquifer is that the GPR found. It kind of obscures the isotope signature, and it has this really funky wave. So we're wondering if maybe the liquid water is altering the isotope ratios in the solid samples that were collected that year. So that's probably where we're going next.
Cool, thanks, Jason.
Alrighty, are there any more questions? We've got 2 minutes until the top of the hour.
Well, if no more questions, I want to truly commend all of you again this year. You were a phenomenal group this year. So fun to have you up on the ice. Sorry I didn't get to see you as much as I had hoped. The weather was not conducive to getting back to the ice field for a few times, but hopefully I see many of you at AGU, and yeah, truly phenomenal to have you join the cryosphere community with us this year. So thanks for all your efforts today and during JIRP.
Yeah, a huge thank you to everyone who's presented tonight. It's been a fascinating set of talks. I love the idea of using the sort of, I want to call it tie-dye. It's not the right word, but those are amazing pieces of artwork.
Alrighty. Well, I guess there's nothing else to say. People can start logging off. And Seth, there is going to be a JIRP showing at AGU this year.
There are at least 7 presentations related to JIRP at AGU this year, maybe 8.
There will be a list put out. If you go to juneicefield.org/AGU, you can put in your presentation and we will publish the list.
And I also suspect we will have a JIRP gathering as we
Monday night.
Monday night. There we go.
Stay tuned.
Whoop, whoop. All right. Well, I will be in Chicago this year for AGU, so hopefully I get to meet you all in person.
All right. Thank you all.
All right. Thanks, folks.
See you, everyone.
Thank you. Bye-bye.
Thank you.